1.7 talking about function notation, specifically right now, all about how we can use it for evaluating. Down the road, we'll talk about it in terms of graphing, and then we'll also talk about it way down the road in terms of finding inverses or composition of functions, stuff like that. For today, just evaluating, getting ourselves comfortable with working with what it means. Okay? So, function notation is a way of writing equations that relates the input, which we should know as x, domain, and even the independent variable with the output being y, the range. The dependent variable, y is determined by x, it depends on x. Ideas like that. Independent variable, dependent variable, new words kind of apply to some old concepts. Here's an example of a function written in function notation. You maybe have seen an equation written like this. Okay? We don't want to write it like that though. With function notation, we replace the y with f evaluated at x. And there's some different things here. That f is the name of the function. We could call it g of x, okay? And that g would be the function's name, okay? We have our input. X is the input. Wherever we see the x, that is our input. The output is whatever f of x is equal to, okay? This is the output. Okay? So we read this. This is read out loud at f of x. That means our function f here is 5x plus 3. So that function f evaluated at x of x equals 5x plus 3. That's how we would read this out loud. The most important thing is this idea of x is the input. X is what we're going to put in the function. Whatever we see in these parentheses is the input. It goes and replaces that x spot. Okay, so that's when we talk about evaluating functions. We're talking about inputs and outputs. We have two ways to evaluate a function. Okay? We already said that the input was x. So if we see a graph, that's one way we can evaluate a function. So our first way to evaluate, which we use when we're looking at a graph, is just to read the graph. Determine the x value, and then find the point. Okay, so determine what the x value is, and then find the point for that x value. So if we look at this first example, the first ordered pair, or the first evaluation we need to do is f at -1. Well, the input here for -1, excuse me, for f at -1 means that x is -1. So here's on the x-axis where x is -1. The ordered pair for that point, the y part of the function, x is taken care of. Y is the f of x. That's what the function evaluated is. That's this point. The y value for that point is 2. So f at -1, when x is -1 for this function, y is 2. F of x is 2. For 0, it's 1. And for 1, that's where x is 1, the function has a value, y has a value, f of x and y should be thought of very, very similarly. That's -3. Okay, so this function is evaluated at f at -1, where it equals 2. F at 0, where it is 1, and f at 1, where it's -3. Okay, there's two examples for you to try here. Look carefully. Figure out x first. Just figure out what x is. Then go from there. Okay? Okay, so let's check it out how you did. So looking at this, in the first one, f at -2. -2 is right here. We go this blue line at -2. At that blue line, we go all the way down to -6. For 0, the function is up at y equals 2, and for negative 1, it's at 1. Okay? So we have some evaluations here. Okay? And the next one, at negative 6, the function is down at negative 1. At negative 2, we are up at 3. And at 2, we are also up at 3. This information, this negative 2, negative 6, just going to go through all this. That means our graph has an ordered pair at negative 2, negative 6. We have an ordered pair at 0, 2. We have another ordered pair at negative 1, 1. That should look familiar. Negative 2, 6. That's this ordered pair is negative 2, 6. Okay? 0, 2. That's this ordered pair. Function notation relates those input and output and helps us write ordered pairs. Here's another ordered pair, negative 6, negative 1. Negative 2, 3. 2, 3. Function notation, very, very useful for writing ordered pairs. So if you have a graph, you're looking for points on the graph based on what the input is and what the output is on the graph. The second way of evaluating is substitution, right? The number in parentheses will be substituted anytime we see an x. We are using replacement, so we are substituting. The input, the number in parentheses, is substituted for x. It replaces any x in the original function, okay? Let's look at how this works. Let's say we have a function where f of x is x squared plus x plus 3. Kind of a boring function. If we want to evaluate f at 2, well, wherever we see that an x now gets replaced by a 2. So we have, instead of x squared, we have 2 squared plus x. Well, not plus x anymore, plus 2 plus 3 at the very end. So 2 squared is 4 plus 2 plus 3. That means this function, f evaluated when x is 2 with an input of 2 is 9. Okay? So you are substituting, you are replacing. There's a bunch for you to try here. Give yourself a good shot at them. Your calculator needs to be in degree mode for the last one. So push pause and make it happen, people. Okay, let's see how you did. Hopefully you show that substitution step of putting 0 in for x, of putting half in for x, of putting 3 in for x. Because then it makes it a little bit easier to calculate. 0 minus 7, negative 7. 4 times half is 3, 3 minus 7, negative 4. 4 times 3 is 12, minus 7 is 5. Okay? Once we substitute it, it becomes a lot easier to calculate. It's just order of operations. It's a matter of replacing the x that sometimes gives people trouble. Right? If we were going to graph this, we would have an ordered pair at 0, negative 7. Because we know what x is, and we calculated to find y. Running through the rest of it, be careful in number 2 that x squared is made negative at the end and not until then. Square first and then make negative. So 6 squared is 36. We make it negative. Then take away 2 more, becomes negative 38. Negative 6 squared is positive 36. We make it negative, and we still get negative 38. Negative 36, take away 2. 0 squared doesn't matter if it's negative because that's just 0. Take away 2 is negative 2. And then we got some sine, cosine, and tangent. If your calculator is in degree mode, you should have done just fine. You're just going to punch in that you need the sine of 30. Sine of 30, once you got that calculator, is 1/2. You would have an ordered pair at 30 degrees with a y value or a function value of 1/2. Sine of 45. You may have got from your calculator 0.707. Some of you may have remembered it's a square root of 2 over 2. Sine of 60. Got from your calculator 0.866. Some of you brilliant people may have remembered that's the square root of 3 over 2. Okay? The decimals are fine. Totally fine. The substitution is more what I'm concerned about here. Look what we did here. This 30 went in and became 30 that we're going to take the sign of. This negative 6 became negative 6 in that x squared. Still became positive 36, and then we made it negative, of course. So for functions, you're either looking at the graph or you're substituting. Okay? The number in the parentheses will tell you what x is. You need to be able to kind of pick out that number and then do with it what you're supposed to do. That's the tricky part. What is x? How does it get substituted? Function notation is pretty simple, at least at what we're doing with it right now. It does get more complicated, but for right now, we're just talking about how do we replace information. We could put, in this last one, our last function here, oops, my bad. We could evaluate f, I don't know, at a bag of Skittles, or a S thing. And that means we would take the sign of a bag of Skittles. Because that's what the input said to be. We're just substituting with whatever the input is. If we go back, function notation is meant to relate input and output. Relates the input. Where's my highlighter at? Highlighter. Highlighter. Okay, relates the input. Oh, dang. Input with output. We substitute in what it tells us to substitute. The answer that we get is the output. Helps us write ordered pairs, right? That's why that XY connection comes in. So function notation, not overly complicated. Just please be careful with identifying the input and then working with the input.